LucidLink is a log-structured distributed file system designed to leverage object storage as a file space, a global namespace, and persistent mount point across virtually any operating environment. In this video, we'll integrate Microsoft Azure Blob storage into a file space. So to begin with, we'll get started within our LucidLink dashboard and portal. We'll create a new file space and we'll select Bring Your Own Storage, where we'll provide a name for our file space called Azure. We'll select Azure from our storage providers and we'll choose a region which is going to be closest to our workload. We'll select France Central. We won't provide a container, however we could provide our own container name. We'll let LucidLink create a globally unique identifier. So we'll select Create, and we're going to need some storage account keys. We'll create a storage account for our workload, selecting a resource group, and we'll use our storage account name LucidLink and select our France Central workload with Blob storage as the account kind and locally redundant storage. We'll review and create, where we'll pass validation and we'll create our storage account. So now that our storage account is being deployed, we'll go back to our Filespace portal, where we can see we're ready to initialize our file space. Once we initialize our file space, we need to perform this from the client side, as the data is encrypted with end-to-end client-side encryption. Only you know the keys. The storage provider and LucidLink has no access to your data. So in order to initialize, you need to download and install your LucidLink client across Windows, Linux, or Mac OS. We've already installed it on our desktop, so we'll launch our client, where we'll be asked for our storage account and our account key. Our account should have deployed, so we'll go to our resource and we can scroll down to our access keys. We have two access keys to choose from. We'll copy the first access key 1 to our clipboard and we'll go back to our LucidLink client and use LucidLink as our account name, pasting our access key and selecting Next. Our root password is what is used to encrypt our file space. So we'll choose a encryption key which is stretched to AES 256 encryption strength, and we'll submit our initialization. Once we submit our initialization, we can open our file space and we can see a mount point called Azure on our Windows machine. Go into our Azure storage account containers. We can see we've created the Azure file space globally unique identifier. If we look inside, we have no blobs. Our file space is empty. So to demonstrate how we write into the object store as a log structured distributed file system in our unique block level manner that enables us to stream individual blobs as requested, we will create a basic text file. We'll call this text file data and we'll put data within it as a simple first step. Save it, close it, go back to our container and press refresh and we'll see a blob. If we download this blob and open this blob in Notepad, we won't have access to the data. The data within the blob is encrypted. We can only access the data from the client side with our credentials for our file space. We divide our data up into individual blobs. Each OS client, Windows, Mac, or Linux, participating in the file space, the global namespace, has a persistent mount point injected into the operating system that streams the data on demand while liaising with our metadata. synchronization. Therefore, we don't have to move entire blobs. We can move a portion of data when requested while the application liaises with the metadata. We separate the metadata from the file data, so all OS clients have a copy of the metadata, but they interact directly with the blob data within the storage account container. We're a log-structured file system. Therefore, as we make changes, for instance, I'm on my Windows machine, so I'll change data to Windows and press save, close. We'll see a new object appear. Now, any objects that have expired from the metadata will be garbage collected. So we use the object store in a very efficient manner. Being log structured, it provides a perfect opportunity to snapshot our data, to enable us to revert to a prior point in time. Now we've got two types of snapshots. We have our snapshot policy, which runs automatically in the background based on defined schedules of either minute, hour, day, week, month, year, and specific retention periods based on those schedules. Or we can trigger a manual snapshot. I'm going to initiate a manual snapshot so that we have our file space on our Windows machine as it is now. We'll also introduce a macOS client and a Linux client. However, before we do that, let's introduce some users and share some specific data to our users. Therefore, we'll create a couple of folders, one called data and one called users. Within users, we'll put a macOS folder for our macOS user, and we'll put a Linux folder for our Linux workstation. We'll move our data text file into data. We know it contains Windows from our Windows instance we're currently on. Let's add a user ACL to our file space. So we'll manage our users and open up our shares and users, where we know this is a fresh file space which we've just created, so we'll have to add a couple of users. Now we'll add our macOS and provide their own password, and our Linux user and provide their own password. And we need to define some shares that we're going to present the data to these specific users. We don't want to provide them full root access to the entire directory structure. For our macOS user, we'll provide read-write access to their own nested folder within users and add share. We'll do the same for our Linux user in read-write, and we'll stop at this point because we'll introduce our macOS user and we'll see how dynamic our share propagation across the file space, the global namespace. So we log into our macOS instance and join the same file space called Azure.filespace with our macOS user and their own password. We'll see a mount point appear within macOS that provides only the access we've specified in our share to our ACL user. So we want to add another share access path to our data. We'll provide data to our macOS user in read-write, and we'll see that data path propagate across the metadata across the file space. On this data share, we'll also add our Linux user, but we'll only give them read privileges, not read-write. So if we're on our macOS machine, if we open up our data, we can add within our data file, macOS, close it and save it, and we know that when we open it on Windows, we can see macOS. The authoritative copy of the data is the object store, the Azure storage account, and Blob container. Now that we've made a change on macOS, let's snapshot our file space again. And let's introduce our Linux user, where we know when we join the file space called Azure Filespace with our Linux user with their own credentials, we'll note that they only have access to their own nested user folder with read-write that we provided them and the data folder. Now the data folder, we know we only provided them read-write, so they cannot delete. However, we can promote them as quickly as we propagated the share for our data to macOS by changing their privileges, their access rights, and we can edit this file and add Linux to it. We've made a change, so I'll perform a snapshot. We'll go to our macOS. We can see it contains Linux, and on Windows we can see it contains Windows, Mac and Linux. We've created a file space leveraging Azure Object Storage where we're writing in our unique block level manner into the object store. We're creating new objects as we're making a change, so we're not downloading entire objects and re-uploading entire objects. We're a log structured design. We've performed snapshots along the way, so out of these 4 objects, 3 of them are going to remain, and our garbage collection scheduler is going to remove the first object within about 10 minutes. So approximately a minute or so's time. So let's, for instance, mount our snapshots while we're waiting. Let's open up on Windows our snapshot in our dashboard, and we'll see a mount point appear called Azure Snapshots, where we can see the 3 individual snapshots we created. The first one reflects the point in time on Windows that we hadn't created the directory structure and data.txt only had Windows within it. If we look at our next snapshot, we had created the directory structure. We had shared to macOS and to Linux, and we'd added on macOS into our text file. If we look on snapshot number 3, we'll have macOS Linux also reflected. The snapshots are read-only. We honor our ACLs across our snapshots. So for instance, if we join our snapshots within our macOS and our Linux, we see the snapshot mount point appear, and we'll honor the directory shares where each user can only access the data in the snapshot in read-only, the data that was shared to them. So we've now provided enough time for garbage collection. Let's go back to our container and we'll press refresh, and we're expecting this object to disappear. So our object has been garbage collected. The remaining objects are protected by the snapshots that we initiated to reflect the points in time that we want to ensure we've got data access to recover data from either a malicious incident or an accident within the file system. So we've demonstrated Windows, Mac and Linux contributing to the same file space and global namespace. Let's add some real-world data. Let's, for instance, open up our task manager so we can see our Ethernet traffic. Let's bring up our dashboard and let's keep it always on top so we can see our remaining uploads. Let's copy a video file. This video file is 20 gigabytes. So we're on our Windows machine. If we right click and copy and paste it within our data directory, we're going to see our copy begin. Now LucidLink caches on the client side as well. The default cache being 5 gigabytes. It's a 20 gigabyte movie. Therefore the first 5 gig are going to read and write into the cache. At about the quarter mark, we'll see the data drop down to essentially wire speed. We're sending the data and we're queuing data in our cache. Data is going to our storage account container. If we press refresh now, we'll see a series of block blobs being created based on the data layout. The copy is halfway, however the data has not yet finished uploading. We've got 2.3 gig of data still in the cache. On Linux, however, if we close our data text file and press refresh, we'll see our movie, where even though we haven't finished copying and certainly haven't finished uploading, we can already begin to start playing the first 37 minutes of the movie. We can also seek to various parts, because as the application is liaising with the metadata, it's drawing individual block blobs from the storage account and container. So now that more data has progressed, and we had 37 minutes that we can seek and skip through, if we close our movie and press refresh again and open up our movie again, now that the copy has finished, the upload has not, we can see we now have an hour and 6 minutes. We have 2 gigabytes of data, 1.6 gigabytes of data yet to upload. We're sending the data at approximately gigabit connection from our server. As we seek through the movie, we can access individual sections that we haven't accessed before through our prefetcher, where we draw the data we need when we need it in parallel TCP/IP connections to the storage account. So now that the uploads have finished, we can close the movie and open it again, and we'll have the whole 130 minutes, which we can start seeking through and accessing the data we need. Now note, when we're playing the movie, we can see it's 20 Mbps. If we seek to another area we haven't accessed, we'll see a spike of 249 Mbps. If we move to another section, we'll see another spike, because that's the prefetcher that's anticipating where or what data we need next. But then it goes down to idle streaming of the individual blobs we need. So I'm going to leave that movie playing. And on my Windows machine, I'm going to introduce some real-world workloads. Some workloads at a server level. To do that, on my Windows machine, I'm going to change my mount point. I'll change my mount point by dropping to the command line where we have our Lucid CLI, which is the same across Windows, Mac, and Linux. On my Windows machine, however, I'm going to perform a Lucid unmount and a Lucid mount using L drive as my mount point. So now I can see on my server I have a persistent mount point called L drive that my server believes is local, but as we know is backed by Azure Blob storage. For this specific workload, I'm going to copy into my Filespace a SQL database. Now this SQL database is 1.2 gigabytes of data. I'm also going to create a very high transactional workload. So I'll set that up now. I'll create a Hyper-V folder. This Hyper-V folder is where I'm going to install a virtual machine. So we're going to have a SQL workload, a virtual machine. Meanwhile, on our Linux machine, we're playing a movie out of the same file space and Azure Blob storage account across different operating systems. Let's open up Hyper-V Manager and let's create a new virtual machine. Very simple. Let's call it Windows. We already have a Linux one. Let's store this virtual machine on our L drive under Hyper-V. Select folder. Next. Generation 1. Add some memory. We don't need network. We will create a hard drive in the same location on L drive. we will use media. We'll choose our Windows Server 2016. We'll press next and finish. So we'll now boot up our Windows virtual machine and we'll begin the installer. If we connect to our virtual machine, we can start our virtual machine, where our virtual machine will launch. And if we look inside our Windows directory and go to our virtual machine, we'll see our memory state. Now, of course, that is a sparse file, so nothing uploaded at that point other than what will be in the VM state when we start using the virtual machine. If we move to our virtual hard drives, we can see our VHDX file, and we can begin and kick off the installer, where we'll do a very basic and quick install, choosing our Windows standard desktop experience and installing on our VHDX file for our virtual machine. So while that's installing, we'll open up SQL and let's attach our database. On our server, if we go to databases, we'll want to attach a database. We'll choose the database that we're going to attach off our L drive. Under SQL, we've got contacts MDF, which is L drive, contacts MDF, and contacts LDF for our log file. If we select OK, we can now open our tables, which contain a number of contact records. So I'll select the first 1,000. Now, I know within this database there is 10 million records. So I'm going to add a number of zeros to our query and press execute. At that point, we'll see our query running against our database. So we can see we've currently drawn down just under 1 million, 1.5 million, and our query is running quite happily. So we can see the data coming in, and we're up to 2.7 million. Meanwhile, our virtual machine running in the background is at 51% of the installer, and of course on Linux, our movie is still playing. Our query is at the halfway point. We can see that data is being read as well as data is being sent to the Azure storage account and into our blobs in our container. If we look and do a quick refresh, we can see our blob block level layout where we're accessing the data in a random access read-write manner. When we go back to our SQL query, we're at the last stages of our query, and with approximately a few more seconds to go, and our query should finish at just under 10 million records. On our Windows install, we're at 75%, about to do a reboot to complete our installer. We can see data being uploaded, and we can see our connection for data being read as well as data being sent to the storage account. So this is demonstrating server workloads and the high transactional workloads that can operate out of Azure Blob storage. Applications believe the data is local. We're reading, we're writing into a local cache and asynchronously sending the data, but drawing the data that's requested when it's requested through parallel TCP/IP connections with the storage account. So we can run real-time workloads and stream the data on demand. Once our installer has finished, we will perform a reboot, and we'll have a virtual machine running out of our Filespace mapped as L drive, where we have a SQL database, we have a Windows virtual machine that we've installed and configured to operate, including the virtual machine resources, directly from a LucidLink file space out of our Azure storage account. We'll do one final reboot after it's detected the hardware, and we should be now prompted for our password. And remembering, of course, a virtual machine does not boot sequentially. Across the VHDX file, which is approximately 10 gigabytes in size, we're doing random access of the data, plus sending data up based on registry hive and page file, because this is a vanilla Windows install of the Windows ISO. So this machine is now operating entirely out of blob storage and drawing individual block blobs that are required when required. If we look at our Hyper-V manager and press refresh, we can see that this virtual machine has been running for 1:30, and we're now ready for the final selecting of our password and logging in to our virtual machine, which is running entirely out of blob storage. So now that we've got our desktop, if I pause our movie on our Linux machine, we'll see entirely the I/O that's required for our Windows machine. So we can see we've got 172 and 35 Mbps down with 28 to 27 Mbps up. Once our desktop appears and all the services start, we should see our virtual machine go down to idle. Of course, after Server Manager loads. I'll cancel Server Manager, and our machine should become idle. And there it is at about kilobits per second. So when we open up Explorer, we'll jump back up to Mbps. As we browse the virtual machine or open any programs, such as Internet Explorer, we'll see it jump back up, because these are areas of the virtual hard drive that we haven't traversed. So Internet Explorer is going to load. We have no internet. I'm going to power down our virtual machine. We saw in the final stages of our install, it was 1:30 to boot up to prompt for our password. This time, however, when we start our virtual machine, we're going to be running out of cache. So I've powered on our virtual machine, and let's ignore the first 6 seconds because of the CD prompt. And after 15 seconds, we're ready to log in to our virtual machine, because we've drawn the data we need from the blob storage, and we're operating portions of the file system out of cache. So of course Server Manager is going to load, the machine's going to behave a lot more as we expect. So in this video, we covered off creating a storage account for Azure Blob with LucidLink Filespace. We introduced Windows, Mac, and Linux, and collaborated and demonstrated our granular snapshots, our garbage collection. We also streamed a video before it had finished copying from Windows. We streamed it on Linux and were able to access the individual block blobs that were available to us, and of course the metadata that had synchronized across clients. We then introduced a server workload, two server workloads. One of them a database and one of them a high transactional workload, being installing, configuring, and running and operating a Hyper-V virtual machine out of Azure Blob block storage. Thank you.